In this problem, we're asked to perform the quotient of a complex number w divided by another complex number z and figure out the result, graph the result, and then talk about some transformations that are happening here. So I'm going to go through each of these in part, but the preliminaries, we can kind of skip through this part a little more quickly. And this is what I mean, this stuff right here. We've been doing this in previous videos, and you can also just look at it in the graph, right? They're written in the graph for you. They're very easy to see. But I'll just remind you that the way you find modulus is by doing the square root of the real part squared plus the imaginary part squared, kind of like a Pythagorean thing. And then the way you find the argument, that angle, is by doing the inverse tangent of the imaginary part over the real part, which is kind of a SOHCAHTOA thing. So if I look at w, which I have here in red, I can either use these formulas, being particularly careful right here. When you do inverse tangent, you have to make sure you're in the right quadrant. And this, because it's negative x and positive y, is quadrant 2. Because inverse tangent could tell you quadrant 2 or quadrant 4, so you got to watch out for that. But if you're just looking at the graph, you can see this is pretty obviously 2 pi over 3 right here, and the radius is 4. Okay, so we can just put those things directly in here. And for the next one, z, likewise, this is pretty obviously 5 pi over 4 as the angle and 2 as the radius. So I can just put those right in here. But if you like, you can, as an exercise, go through and see if you can figure those out from the information that is given, and just pretend the graph doesn't exist, so you don't look at that for your little cheats. So now, going on into step 2, I want to use de Moivre's quotient theorem to determine the modulus and argument of eta, this n with the little tail on it. Basically a quotient. So the first part is very easy. What is w divided by z? Well, that's 4 divided by 2 if I look at the magnitudes. And 4 divided by 2 is just 2. Okay, so that's how I got here, 4 divided by 2. And then for the argument of this one, this is also pretty easy. All we have to do is subtract. I'm going to draw this in blue because I'm going to be plotting it. I want it to be distinct from the others. So here we have 4 divided by 2 equals 2. For this one, we have the angle of w, which is 2 pi over 3, subtract the angle of z, which is 5 pi over 4. And it's not enough to just say that. You can't get away with that. You're going to need to actually do some, subtraction with uncommon denominators. So get your common denominators, and what are we going to end up here? Well, let's just do it. Let's just do this out. 12ths is what I need on the bottom, so I multiply the first fraction by 4 over 4 to get me there. This becomes 8 pi over 12. And the second fraction needs 12ths, so I multiply it by 3 over 3. So that's going to be 15, I think. 15 pi over 12. Great, 15 pi over 12. So 8 pi over 12 minus 15 pi over 12. And if you put in here as your answer, if you write in negative 7 pi over 12, it will be marked wrong. And I hope you can see why it's going to be marked wrong. It's because we want an angle between 0 and 2 pi. So what do we have to do? We have to take this thing, and we have to add 2 pi to it. So in other words, I don't want a negative angle. I'm going to find a positive coterminal angle. And when you add 2 pi to this, you'll realize we don't have negative 7 pi twelfths. We have 17 pi twelfths. Now, writing the polar form is really not hard. You just take the magnitude, which we found, 2, and you take the angle that we found, which was 17 pi over 12, and you put that in here. Okay, and then we've got an I times sine, but again, it's 17 pi over 12. And that would be our polar form. Now, in terms of marking this on the graph, I think the only tricky part about this is it's not really obvious to me where 17 pi over 12 is. That's not one of those angles I just happen to remember. But if you convert it into degrees, what you would get for this is 255 degrees or something like that. Anyway, it's going to be right around here. This is where 17 pi over 12 is. And remember, the modulus of this thing is 2. So there we go. There's our number, if we draw it on this plane, and if you think about what this represents, what we did here was we divided w by z. So the very first thing that I like to imagine is dividing by the magnitude. You have this big long number right here, which is 4. Dividing it by 2, it's going to get smaller, so it shrinks. That's the first thing that happens when you're turning this into a quotient, right? It shrinks like that. And then the second thing happens, when I divide, that's subtracting an angle. So this angle right here, see that big angle? That's how far this has to get rotated when you bring it around. So it gets rotated clockwise in that direction to our final landing spot. So how do we say that? Well, I'm doing a clockwise rotation by, and remember this is transformations on W. So what's happening here is I'm transforming W by dividing it by Z. So it's doing a clockwise transformation, clockwise rotation by 5 pi over 4. Where is that? Here we go. Clockwise rotation by 5 pi over 4. That was Z's angle. And a scaling by a factor of 1/2 because this thing's getting smaller. Okay, so a scaling factor of 1/2. And there we go.